Hello, and welcome to the 10th video in the C++ for Beginners series. In this video, we will continue working with arrays and vectors. So let's get started. First, I'm going to quickly talk about type inference. Type inference is the ability of the compiler to deduce the type of a variable based upon its initialization. The auto keyword, which is redefined in C++ 11, uses type inference to determine the data type for a variable. As you can see, we're defining x as a double data type, assigning it the value of 33.3. But y is determined by the compiler as we're assigning y to the value of x. So since the compiler knows that x contains a double, it also makes y, or deduces that y should also be a double. We can also use auto to determine a variable's type directly, such as initializing variable x with a literal integer 5, and variable pi with the value of pi. If we use the type ID function on the variables, we can display their data types. So let's look at some example code. I have some example code here to help demonstrate the previous slide. I have our two variables, x and pi, which both use the auto keyword for the compiler to determine their data types based upon their initialization. I'm also going to briefly show another type inference, the dect type keyword. Similar to auto, but instead it extracts the data type from an existing variable or expression. In this example, we are setting the variable d to the same data type as x, and I'm assigning d the value of 8 times 2. Then I have some print statements below to help display the data types. I'll talk about the below code in a moment, but first let me compile and run to show what we just went over. But first, now may be a good time to point out that you should have code blocks set to use the C++ version 14 to follow along with the rest of the videos in this series. To do this, simply go up to Settings, Compiler, and make sure the box is checked next to have G++ follow the C++ language standard. So just go ahead, if it's unchecked, check it, and click on OK. This setting does take effect globally, so all your projects will use this flag going forward unless you go back and change it. Okay, with that set, we can now compile and run the code. And here's our output. Notice I'm not displaying the values, but I just was concerned about the data types. So here we see data type of variable x is integer, which we can see since we assigned x a 5, it's a literal integer. And we can also see that the data type of variable pi is a double, since again we're using a floating point 3.14159. And finally we can see that the data type of d, dect type, is also an integer. That's because it derived its value from x, which is also an integer. Okay, now let's go look at the rest of the code. So we won't be using dect type too much, but we'll begin to utilize the auto keyword quite a bit going forward. I also want to talk about a range-based for statement. Starting with C++ 11, we can use range-based for statements to iterate through a range of data. Common examples include initialization lists, arrays, and vectors. This is similar to the for loops we have been using, but it has the benefits of being a bit easier to read, and we don't have to worry about determining the size of ranges like we did with the array example in the last video. Don't worry though, there is still a place for loops. This doesn't replace them, but it is useful for when you want to extract items from a range of data. So we can declare a for statement as shown on the slide. For range declaration, colon, range expression, then our loop statement, similar to the for loops. Range declaration is a variable that will hold our values as we iterate through. And range expression is the actual range that we want to iterate through. In the example, I've created an array of 5 elements named simply array. The for statement is using the auto keyword we just went over to set x as whatever data type the array elements are. In this case, they're integers. The colon is used to separate the parameters, with the second being the range we wish to iterate through. In this case, our array name simply array. Then a simple output statement to print the elements as they are retrieved displays the output shown here. 1, 2, 3, 4, 5. Switching back to the code, here's the example I just went over in the slide. Again, we can run it and see the results. And just like in the slide, here's the output 1, 2, 3, 4, 5. Okay, let me move back to the topic of arrays again to cover multidimensional arrays. I'm not going to spend a lot of time on this, as it is very similar to one-dimensional arrays, but we can expand our arrays to hold more data. This slide shows the basic concept. So with the one-dimensional arrays we went over in the last video, you could think of them as simply a row of sequential data elements. Each element also could be thought of as a column of data within that single row. So if we created an array with 2 dimensions, we can now represent that data as being in the form of a table. This example shows a 3 by 5 array of data, or 30 elements in total. We declared an array like before, but with the addition of an extra set of square brackets. Also like before, we need to set the size at some point, when we declare the array or during initialization. Here the size is set to 3 and 10. So you can think of this as rows and columns, with the rows being set by their first value and columns being set by the second. And yes, you can extend this to 3 or 4 dimensions, but for now we will just stick with 1 and 2 dimension arrays. But, however, you could think of a 3-dimensional array as a cube of data, or perhaps a stack of tables layered on top of each other. Let's go back to the code. I have some code ready to demonstrate using 2-dimensional arrays. I've created an array named R and gave it a size of 3 by 3 elements. So like with a one-dimensional array, we can initialize it multiple ways. The first is assigning a list of sequential values. Once one row fills up, it moves on to row 2 and so on. I'm going to leave the first line commented out. We'll assign our array the second way. This is the exact same way as the first, but it's just a little bit more easy for us humans to read and understand what's going on. So then we're going to retrieve the contents of the array using a standard for loop. Notice though, we need to use a nested for loop to handle the rows and columns, with the outer loop incrementing through the rows and the inner for loop incrementing through the columns within each row. We can then use the row and column values to access each data element within the array. Below that, I'm using a range-based for statement to do the same thing. Do notice though that I needed to dereference the row declaration since we are just using it for an indicator of the row we want, which is actually good practice anyway. Let me just go ahead and compile and run the code. And here you can see our output. In the first example, we're displaying the contents using a for loop. Second example, we're using a range-based for statement. Notice they produce the exact same result. Range-based for statement is a little bit easier when we're working with arrays, especially when we get to multidimensional. And finally, I have another example, the same range-based for statement, except modified to be read-only access, by using the constant keyword, which specifies the variable cannot be modified, and we're dereferencing both variables. This doesn't work if we want to modify the elements, but it is a good practice for read-only type operations like this, where we want to avoid accidentally modifying the data. Go ahead and compile and run it. You can see we're getting the same exact results. And finally, I just created a simple one-dimensional array example to maybe more clearly show the operation of the range-based for statement. Go ahead and compile and run it. And here's our output of the array 1 through 10 as you'd expect. Notice that the for statement is a little bit cleaner to see just using a simple one-dimensional array. And also notice, just like in the last example, we can dereference. And we can also make this a constant type. And of course, instead of specifying integer, you can also use auto. Okay, so I believe that should be more than enough about arrays. But the good news is that these important concepts have given you a strong foundation to build upon as we switch over to vectors. Vectors are much like arrays, except even better. Vectors are part of the standard template library, often referred to as the STL. They're part of the standard namespace too, so you need a prefix with std::, just like we do with cout. To use a vector, we need to be sure to include a vector header at the top of the program. Create a vector using the keyword vector, the data type, and the name of the vector. There are many member functions we can use with vectors. A couple are size, at, and resize. We'll be looking at many more functions very soon. Let's jump over to code to get a better idea. Okay, first we have to use the include statement to use vectors at the top of your program, so just include vector. I have an array here. That's just to show the similarities between arrays and vectors. The vector is created much the same way, but with a bit different syntax. It's part of the standard namespace, so I need to prefix it with std::, like we do when using cout. So we use the format vector, again knowing the standard prefix if you're not using the namespace standard statement at the top of your program. The data type, in this case we use an integer, and then the name of the vector, which I'm just simply calling my vector. Also just giving it some values right away. Notice also that we're using angle brackets or greater and less than signs to enclose the data type. We do not need to include the size like we did with the array, because vectors will automatically resize themselves to adjust their needs as the data grows. Below, I just have some output statements to show how we can access the data within a vector. The first one just prints out our array. I only included it to show the similarities and differences to vectors. We can print out the array with a standard for loop. Notice though, we need to get the array size ourselves. Remember, we need to divide the array size by element size to determine the length of a standard array. Here I'm assigning it to the variable n, which is then used in the for loop. The vector for loop, however, uses the vector size function, making this operation easier by returning the number of elements in the vector for us. The vector size function returns its value as an unsigned integer. It's best to compare like data types, so we're using an unsigned integer in the loop's initializer section. Remember that a normal integer, or int, is signed, which means it can be negative or positive, where an unsigned integer can only be a positive number. So making the comparison between two unsigned values ensures no problems will pop up later on in the code. For this simple example, it probably would not matter, but it's good practice to get used to. So in the first example here, we're using square brackets to actually specify the data element in the vector that we want to access, just like we did up in the array. In this case, we're using our iterator I, as we normally do when using for loops for this. The next example, we're using the vector's at function. The vector's at function is going to return the element at a specified index I, which again is our iterator in the for loop. With the bottom one, we can use the range-based for statement to output the contents of the vector, as we looked at in the last video. Going forward, I'm going to be using this for statement much more frequently, especially when it comes to printing array contents. So it's a good idea to get used to this syntax and format. Finally, I just want to go over one more quick example, showing like with arrays, we can declare the vector separately from its initialization. So here I've just created a new vector, data type integer and just simply named it v1. Then later on in the program we could actually initialize it with values. Here I've just simply given it 12 values. And again, a simple range-based for statement to print out the contents of the array. So let me go ahead and compile and run the code. And here we can see our output. Top line again is just the contents of the array. Next we see the results of the size of function. Again, our first vector was the size of 5. 5 elements, so size of returns 5, which we then use in our loop. Then we have the 3 examples of the different output statements. So the first one we use the square brackets like we did with the array to achieve the individual elements value. Second one we use the vector at function. And the last one we're using our range-based for statement. Then finally down here we have the contents of the new vector, vector1. And it simply prints out the values. Okay, so that was a quick introduction to vectors. I think I'll save the more in-depth coverage for the next video, but for now I just wanted to show you the similarities and differences between vectors and arrays. I will mention that there are dynamic arrays which are closer in function to vectors than the standard arrays that we have been working with, but I'll save that topic for after when we have covered pointers. But for the most part, you would normally want to use a vector anyway, so you should be good for now. Well, that's all for this video. I'll be covering vectors exclusively in the next lesson. So until then, I'll see you in the next video.